All right, good afternoon. Well, welcome to the next session. So next session is about working with real-time data streams for IoT devices and is presented by Lachlan Blackhall. So please welcome Lachlan.
Oh, good afternoon, everyone. Welcome to the session. Look, I think I'm actually really pleased that I'm following the talk that Nick just gave. So Nick, for those of you who weren't here, Nick just gave a really insightful talk, I thought, on some of the problems we have with the Internet of Things. And it's interesting for me to hear this because my background, I'm actually originally an engineer. And so my background's actually as an aero engineer. And as one of my professors once said to us, he's like, the reason you have to be really careful when you're designing and building planes is that when you're 30,000 feet up, your passengers get quite unhappy if things stop working. And I think sometimes it's a really interesting mindset that I don't necessarily see when I move across towards software. It's sort of software gives us the ability to build things so quickly and so easily that sometimes we forget that there actually is a really useful engineering process to be done beforehand. So I'm actually going to be talking about sort of one really specific problem that I see with a lot of data handling in regards to IoT devices. And I hope that sort of motivates sort of a broader interest in people understanding the fact that oftentimes a lot of the problems that we see have already been solved in other disciplines. You just have to go looking for them for those solutions to understand how we should actually apply them in the software world. So for those standing at the back, if you want to come forward, there's still a bunch of seats in here, and I'm sure people will squeeze in for you so that you can have a seat. So aside from being an aero engineer many years ago, I'm currently the co-founder and CTO of a company called Reposit Power. And Reposit builds control and optimization software for batteries. And we have a piece of hardware and some software that actually goes out into the field. And so I've always hated the fact on some level that we've built sort of an IoT device because I really think it's, I have many of the same problems with IoT as lots of you do. But it's really interesting. These are IoT devices. They're boxes that contain a little bit of hardware, a little bit of software, and they're connected often to the internet at the end of very, very skinny wires. And one of the first things that we did when we started the company was we wanted to design everything as though we were blasting it into space. Because if you're in space, you don't get the chance to go and fix it. You've got to make sure that it works. Not only that it works, but that it's robust to communications failures, that it's robust to other errors, it's robust to software errors, particularly when you have humans writing the software. So that's kind of the background that I'm coming from in talking about what I'm talking about today. So particularly in my world, in terms of what we're doing and sort of the broader IoT world, there's heaps of talk around the concept of smart homes at the moment. And so, we're starting to see things like, residential batteries rolling out into people's houses. We're starting to see smart cars. Increasingly, there's going to be access to, partially autonomous or fully autonomous vehicles. We've got smart thermostats. Got smart toasters, which I think is maybe a slight overreaction to the IoT problem. We have smart lights. Again, I wonder if people actually need to know whether I'm turning my lights on or not. But we have heaps of sensors and actuators rolling out throughout our homes. And increasingly they're put there to try and improve our experience of living in our houses. And that kind of then gets magnified into this concept of smart cities. And so you take all these sort of individual actuators and sensors that are in houses, and then you think, well, I could actually put these in lots of other places too. And so you start, putting them in street lights so you can save energy sometimes, and you put them in smart sidewalks, and you end up with smart buildings that are able to regulate their own temperature and the sunlight and tinting and all of those kind of things. And so we're really heading towards this world where we do have billions of devices that are little bits of hardware and that are little bits of software and that are ultimately connected into the internet. And so I suppose we're all going to have to live with the fact that, like it or not, the Internet of Things is going to be here. It's up to us to determine how well we build it, and I suppose that ultimately the value that we get to derive from it. So smart homes, smart cities, Internet of Things, ultimately you end up with a lot of this. You end up with heaps and heaps of data. And I think, I've come out of the energy world, and my big gripe with sort of, smart grid, as it was originally called, was simply the fact that we sort of got to the point where we were like, cool, we can collect data. And so we collected it. And then we're kind of like, ooh, maybe we should do something with it. But we haven't really worked out what. So it worked out, smart grid worked out really, really well if you were a telecom company that could shift data, or if you were a database company that could store data. And I think this is something that I think sort of paralyzes our ability to actually do really clever things with little devices at the end of the wires. Because more often than not, the moment we start talking about this, these are the kind of solutions that people talk about. And with all due respect to these pieces of software, they are absolutely fantastic pieces of software. But they're the kind of software that you need to be running in large centralized data centers. And they require vast amounts of resources to be able to work with these large data streams. And in order to get your data from this tiny little device at the tiny end of the skinniest little wire in the middle of nowhere, you've got to ship it all the way back to your servers so that you can use these kind of pieces of software. Then you turn it around and you send it all the way back to the device at the end of the wire. So, if you're trying to do something smart in somebody's house with their lights, for example, why on earth would you collect the data in the house, ship it like tens of thousands of kilometers to a data center, work on it, and ship it back? And so this is sort of the problem I'd like to talk about today, which is don't think about the world, or the data world in particular, as this large centralized world where you can just always ship everything home. Start to think about what you can actually do with live data streams on devices like this. Tiny little devices, super low power, in the middle of nowhere, that are collecting data. And I think, to Nick's point here, when you are talking about the lifetime, the longevity of batteries in these devices, if you can avoid shipping the data over the wire, you increase the battery life almost indefinitely. And as we've sort of moved from a world of very, very sort of small computational power 40, 50 years ago into this modern world, we sort of abused the fact that a lot of the methods that were developed 50 years ago for handling data, particularly in situ, have sort of stopped being used. And so I'd like us to think about how we can do real-time data processing on reasonably frequent data streams. So, streams that could be multiple samples a second or faster on a tiny little device like this. And I think you'll be surprised at how effectively you can actually do it. It's quite amazing. So when you get to ship everything back to the data center, you often then can hire a room full of people to make your data look like this. And so when you think about what most data scientists like to see, this is how they start their careers. They're like, my data is going to look beautiful. It's going to be clean. It's going to appear every 5 seconds. It's going to have nice timestamps attached to it and all the rest of it. And yeah, I suppose that's true. If you ship everything back home and you hire a lot of really clever people, you can make sure your data looks like this. But when you collect data at the end of a wire, your data looks like this. It's terrible. It's noisy. It doesn't always turn up when you want it to. There were comments before around sensors in servers not returning data appropriately, and that's totally true. Sensors often misread data. Sometimes the data just doesn't come back. Sometimes the data's wrong. Sensors are well known for giving spurious data back, so they might be giving you pretty good readings most of the time, but then all of a sudden they're not, and you get readings that are so outrageously different from the others that they're obviously not true. And I think worst of all, when you have sensors sort of out in the wild, you get lots of noise in a sensor. And by noise, it could be electrical noise, it can be thermal noise. There's lots of different things that lead to your data being really quite poor. And so I'm here to convince you that filtering is the solution to all of these problems. So hands up if you know what I mean when I'm talking about filtering. Cool. Not coffee filtering, if we, yeah. So filtering is a particular technique. It's been really popularized by engineers. And I know engineers are a bit scary sometimes, but we're reasonably friendly most of the time. And so there's some methods that came out of research, you know, particularly one method I'm going to talk about, the Kalman filter, that came out of work in the 60s. And if you take nothing away from this talk at all, it's that if you are dealing with real-time data streams and you are not using a Kalman filter, then you're doing it wrong. And that's not an opinion, just wrong. So I'm going to motivate this with a really simple example. Let's say you wanted to make a smart thermostat. So a smart thermostat does a couple of things. Number one, it measures the temperature. And number two, it tells your heater or your furnace or your air conditioner whether to turn on and provide some heat, to turn off and do nothing, or maybe to provide some cooling in order to reach your set point. So the first thing you actually have to do is you have to be able to accurately measure the temperature, which seems like a really simple problem, except when you start actually using sensors, particularly low-cost sensors that fit onto low-cost computers at the end of a very, very long wire in the middle of nowhere, this is what your data might look like. All right, so you know, in the energy world, we have these devices and we put them in the middle of nowhere and we're reading data off people's switchboards. And it's not uncommon to see data that looks this noisy. Like it's not just, I think we've somehow managed to convince ourselves that data will always come off in a nice form. And I want you to not think that, because it's just never true. Data that comes from real sources in the wild always looks terrible and looks a bit like this. And I would challenge anybody to be able to tell me what the actual underlying signal is in this data set. So to talk about filtering, what we're going to do is I'm going to talk about two particular type of filters. And I'm going to show you ultimately how we end up at the Kalman filter and why the Kalman filter is really useful. And so if we go back to this problem of the thermostat and how we actually measure the temperature, the goal of the thermostat to begin with is actually to be able to turn these measurements into something that you could use to actually then do control on a heater, furnace, air conditioner, et cetera, et cetera. Because if you use these samples here, you would be sending control signals to turn down the heat and then turn up the heat and then turn it off and up and down all over the place. It'd be just totally chaotic. Not only would you likely damage the heater or the air conditioner, you're actually never going to end up with the temperature that you want. And so I'm not going to get into it now, but there's a really interesting branch of mathematics called optimal control. And optimal control is about how you actually get a device to do something in the presence of lots of measurement noise. And it turns out, and the reason I said before it's not an opinion, that it's just wrong if you're not using a Kalman filter, is to do optimal control, you always start with a Kalman filter. And there's really good reasons why, and I'd like to show you. So the first approach we might take to actually trying to extract this underlying signal that we're measuring here is a moving average filter. So hands up if you've heard of a moving average filter before. All right, pretty good. So moving average filter, pretty simple. You take a fixed number of samples from the current sample back, you average them up, and that's a measure of the underlying value there. So you might have a moving average filter of window length 5, for example. So you'd take the current sample and the 4 previous samples, you'd average them out, and you would say that that is the output of your filter right now. So if you were trying to work out what the temperature was, it would be the output of that filter. All right. So you could also have a filter length filter length 30. You could have filter length 50. You could have weird weighting of all the different samples to do this. But ultimately, simple moving average filters, reasonably good. So in Python, so all of this code, there's a link at the end of it. All the code's up on GitHub, all 50 lines of it, or 60 lines of it. I'd encourage you, if you're interested in this, to go and have a look. Because the thing that's really interesting is the code's actually really simple. Like there's nothing clever here. And while I wrote this on my Mac, I think the thing I'd like you to appreciate is there's not even any, there's nothing outside of the core library that's being used in this. So if you're talking about doing implementations on tiny devices, there's no barriers to using this stuff. It's really quick. So the moving average filter, you initialize it with this window length, which says how many samples you're going to keep. every time you get a measurement, you pop it into your list. And if the list gets to, like, you've got to begin with, you don't have enough samples, you just got to work with what you've got. And eventually you reach a point where you're at your limit. As you get a new sample, you pop the first one off because you're appending at the back. So you're throwing away the old samples as you go. When you then want to actually get the current state of your filter, which is the current temperature right now, you sum it, divide it by the number of samples that are there. It's just a straight average, really easy. The second type of filter you might think about is the Kalman filter. Now, the mathematics of the Kalman filter are actually really clever for something that's actually really, really simple. And so I'm not going to deal with the mathematics behind it, because I think we get bogged down in it. But I've put some links at the end that you can go to, and there was a great blog post recently that talked about the Kalman filter and the shape of the filter and what it means sort of mathematically as you're using it. So I'd encourage you to go and read that. But in simple terms, what the Kalman filter says is it says, when I want to update a measurement, I probably should take into account how much noise there is in my measurement. So if there's lots of noise, every time I get a sample, I only learn a little bit more about the underlying signal. So if there was no noise at all, I could trust the signal. So if you had a flat, if I could measure something perfectly, my noise level would essentially be 0. And so I can trust that that is the temperature that I'm trying to read, or the value of the underlying data stream. But if it's really noisy, I can't trust it. That would be silly. And so what the Kalman filter does is it says every time I get a new sample, I know a little bit about the noise structure. You have to sort of tell it that up front. But it's very robust to that information you give it up front. It says, well, I've only learned a little bit from this piece of data. And so it then uses the next piece of data, and it's learned a little bit more. And so the rate at which the filter sort of converges to the solution depends on the underlying noise level. So if there's more noise, it takes slightly longer to converge, but it rejects the noise that's there in the values that it gives. So does anyone have any questions on that? That's probably the most complex thing I'm going to say today. All right. So long story short, the Kalman filter is mindful of how much information it's gathering each time it reads it. And the really interesting thing from the Kalman filter is just that it only needs 2 values to store in memory to completely characterize the data stream. So with a moving average filter, if I have window length 5, I have to store the last 5 samples. If I have window length 50, I have to store the last 50 samples. With a Kalman filter, I only ever have to store 2 values. That's amazing when you think about it. That I can give you an accurate measurement of the underlying value that I'm reading. Sorry, I'm back. The thing I'd like you to take away from this is that the Kalman filter, slightly more complex to implement than a moving average filter, but not super complex. It's still only probably 30 lines of code, tops. And still, ultimately you can implement it without using things outside the core Python library, and it runs blindingly fast. So the beauty of the Kalman filter is actually that it can handle multiple data streams in parallel. And so it's really, really useful where you might be collecting lots of data simultaneously, particularly where you have, say, correlation between them. And so this is a really challenging problem to solve. And so we're only going to solve it in a single variable case. We've just got one data stream. But the power of the Kalman filter is that it actually extends into as many parallel data streams as you want. It still gives you really, really good results. So initializing the two filters is interesting. You know, if you see down the bottom, implementing the instantiating the moving average filter, you just need to give it a window length, which is pretty simple. When you instantiate a Kalman filter, you have to tell it a little bit about the system that you're kind of measuring. But when it comes to just using it for measurements, it's really quite simple. The one thing that you have to, so the two parameters that I think are just worth sort of touching on, just so it doesn't look like I'm doing any magic behind the scenes here. You have to pick an initial estimate. And now the Kalman filter is really robust to your initial estimate. So you could actually pick it, you know, you could start it off at 1 million or 1 billion or 0 or whatever, and it's still going to work. But in reality, if you were doing something like temperature, it's probably a pretty fair statement that you can probably pick an initial temperature reasonably accurately. You don't have to pick it accurately, you just pick a number. So Kalman filter, pick something sensible. Doesn't actually matter what it is, it'll work anyway. But just to show you that you actually do have to pick something. The other thing you have to pick is the amount of noise. So you have to set the covariance, which is sort of a statistical measure of noise. I won't talk about how you do it here, but suffice to say, it's actually, if you sample any set of data, it's actually really, really easy to work out what the statistical noise is there. So with a Kalman filter, it's pretty easy to work out how much noise you have in your system that you can then initialize the filter. So I suppose, again, yeah, don't worry too much about that. It's still, you don't need to actually know anything about a system before you start using a filter, before you start using the Kalman filter, and you still get good results. So you implement these filters, and then this represents the entire processing you need to do on a data stream in order to use the filters. So I created this vector of random data, which we saw earlier, which was plotted. And then all these filters look like, they're all set up to take data sequentially. So you don't get all your data at once. This is like if you were reading off a temperature sensor. You take your temperature reading, you chuck it into the filter, and then you can measure the predicted temperature out. Then you get another sample, you chuck it in, another measurement. So it's really simple. You don't have to keep all your data, you don't have to store it. You definitely don't need to ship it over the wire to a database to then process it. You can do it all in situ in a tiny, tiny, tiny amount of cycles and in a tiny, tiny, tiny amount of memory. So back to our data. So I'm going to show you first the results of a filter that's got it's a moving average filter with a window length of 5. So it's better than the raw data. So it's starting to look a little bit better. Still pretty noisy though, it still sort of jumps around a lot. Probably the key thing you can see out of this is it starts to look like there's a pretty definite point at which we changed underlying temperatures here. So that's useful, it's good to know. Then we try out what the moving average filter looks like with a window length of 50. And now you're kind of like, well, that's actually really quite impressive. Like it's pretty much picked up, you know, the underlying data signal there. So for those playing along at home, the underlying signal was 20 degrees for the first 100 samples, and then 22 degrees for the second 100 samples. And so you can look at you can look at these filters, and the one with 50, a window length of 50, is pretty good. Like it actually picks that up. One of the key issues though that it has is it takes a long time to recognize the change in the underlying temperature. And if you were trying to control your thermostat, that might not be great because it might take you a long time using this filter to work out you have to turn the heater up or you've got to turn the heater down or something like that. And so this is one of the key issues with the moving average filter, is that it's heavily dependent on the window length that you choose. And so you ultimately need to actually know something about your system in order to get it to work properly and to give you really good answers. Having said that, if you were just going to use the raw data for your application, then just implement a moving average instead, because it's a lot better than what you would get if you were just implementing the raw data. But you wouldn't do that, because you would all use the Kalman filter. And so the Kalman filter is the black filter here. And while I didn't hear the oohs and ahs that I was sort of hoping for, you should see that the Kalman filter is actually really quite impressive, given that it uses no memory. It's only remembering 2 things, remember, so it doesn't have to remember any of your past data, so it takes up no space in RAM. It's not only really highly accurate at actually pulling out the underlying signal, but it much more quickly realizes that the set point of temperature has changed. And so it's really easy to configure because you only have to tell it about the noise, not about picking arbitrary window lengths and so on. So I know that when you go home tonight, you're going to be oohing and ahhing in your heads, but really impressive. So I don't have much more to sort of end on. But I really would like you to take away from this the fact that we live in a world where you can ship it over the wire and use a very, very big database to work out what's going on with your data. But we've also got all of these amazing techniques, and the Kalman filter is just one of them, to actually work with data streams on device, on tiny little devices that have very little memory, very little computational horsepower, and you can do pretty amazing things in the home or in the location where your device is. And if you do this, you don't care if the internet works. Because if the internet's only working 10% of the time, it really doesn't bother you because you can continue to perform these calculations. So if your thermostat were to use this kind of approach for measuring temperature, you would be able to control the temperature locally. And you would not need to phone home at all in order to provide a really awesome customer experience by ensuring that the house is always at the right temperature. And that, I think, is pretty amazing. And that's why I think you should all make sure you use Kalman filters in future projects. Questions?
All right.
Thanks, mate. I'm working on a project currently which is all about solar power, and I'm using a little embedded system to measure current usage and whatnot. One of the problems I faced is that measuring current usage uses current, and that introduced noise in all my measuring. Have you come across a similar thing, and is this sort of a filter for that data going to improve my chance? Like, I've tried medians, I've tried all sorts of low pass filters to try to get around that. It's a tricky one for me.
So this will sound really trite when I say it. Sorry. This will sound really trite when I say it. Go home, get the code off GitHub, implement it, and it will work. And it will amaze you that it will work. And the guy who invented it's a genius. So he's only recently passed away, Rudolf Kalman. The filter is amazing. Like, it's mathematically optimal in a well-described situation. So it's mathematically up to where you have Gaussian noise. But it just works in every case. Like, there's just not a case it doesn't work in. It doesn't matter whether you have uniform noise or really random noise or any other shape. It just, as long as the noise is symmetric, Kalman filter will always work. And I'll be surprised if it doesn't fix your problem instantaneously. See ya.
Any more questions?
Let's say you're in an industrial application where the data fluctuates because it's real. How do you separate noise from a signal that's supposed to fluctuate?
I feel like we're going to have a lot of these answers. You just use a Kalman filter. And I know, again, I know it sounds really trite just to always be like, no, just use it, but it will blow your mind. Like, as long as you have the underlying noise measurement, which is really, really easy to get. The Kalman filter, I actually have I haven't told you the whole truth about the Kalman filter, in that the Kalman filter it's not only great for pulling out measurement noise, but it actually allows you to have processes to get very sensible estimates for when you measure processes that have underlying dynamics. So if you were just reading temperature, you're not assuming there's anything that's changing that temperature. But in an industrial standard, say you're doing like something like in the chemical processing or something like that, you can actually model what the chemical processing does, so that That allows you to work out your prediction of what would happen given a particular state. You feed in noisy measurements and you still get really excellent state estimates coming out the end. So Kalman filters are sort of typically seen outside of the engineering world as just a little bit too complex to work with, but they're really not. And sometimes it takes a little bit of time just to understand the dynamics that's going on there and to write the filters for slightly more complex situations. But I'd always encourage you to do it, because once you've licked it, you're never going to have these measurement issues again.
Do you have to keep updating your noise covariance over time? Because you're assuming the signal's stationary, basically, if you're not.
Yeah, so you can. So the base, sort of the Kalman filter is a bit like buying a new car. You can get the base model, which is sort of this model, and you tend to have stationary noise. Yep. There's like so many variations of Kalman filters to take into account where your covariance changes over time, or where you have different types of noise, or where you have, there's unscented filters, there's filters for when it's non-linear. So you just have to match the choice of your flavor of Kalman filter to the problem that you have. And
what do you do if your noise is non-Gaussian?
You use a Kalman filter. And again, I know it sounds really silly to just keep saying it, but it's the Kalman filter is mathematically optimal when it's Gaussian, so you cannot do any better than Kalman. But if it's not Gaussian, as long as it's symmetric, the Kalman filter still works flawlessly. I've never seen a Kalman filter not work just in any situation, actually. But I know it seems like magic. I feel really silly. I don't mean to. It seems like magic. It just kind of is. It's just awesome. It just works really, really well.
I was just wondering if you'd come across the Udacity course on AI that's taught by Sebastian Thrun, because it's basically an extended tutorial on Kalman filters and how they're basically the centerpiece of Google's self-driving car AI. So if anyone's interested in Kalman filters, I'd recommend it.
Yeah, it's a good tip. I'm not particularly familiar with that, but there's a reason that Google and everybody else uses Kalman filters, because it's the right thing to do.
Hey, thank you. If there's an array of sensors spread across geographical areas, and you got to make decisions based on, so will a network of filters be good? Will you still recommend everything in that network be Kalman filter, or is there other ones?
I feel like we all know the answer to this question. Yes. So the Kalman filter is usually implemented as a matrix problem, because it deals with multiple channels. So if you have a network of sensors that all have data streams coming from them, you use the sort of the matrix form of the Kalman filter, which is like basically the same, except division's replaced by the inversion of a matrix, which is still relatively quick. Realistically, once you start moving into the matrix problems, you have to then include, say, NumPy, if you wanted it to be easy. Although the nice thing is that all matrix problems are typically quite fast to run on most embedded devices, because you can reduce them down to addition, multiplication, and division without needing the matrix implementation. So you don't actually need NumPy in order to do matrix calculations if you're dealing with them on very, very small devices. If you're dealing with them on slightly larger devices, so Raspberry Pis and things like that, you can start to use things like Atlas and LAPACK and those kind of low-level C libraries that do matrix computations really, really quick. I'm being asked to stop, so do you want one more question?
So you're saying that you shouldn't bother, in general, sending your raw data over the wire and storing it on a server somewhere. But wouldn't there still be value in a lot of situations in doing that? Because the Kalman filter is, yeah, sure, it's the best way to get a good signal, but you might still want the raw data for doing other analysis later, or as proof of what the raw data was.
Yeah, totally. I mean, I'm not suggesting that we never store raw data ever. I suppose what I am suggesting is just that if you're going to use the data locally to make other decisions or to make, to close the control loop or anything like that, it's worthwhile processing there. It also means that you don't have the problem anymore of needing the internet to be up, because you can still cache all that data and send it up when the internet's available, but you actually have useful data available on device in real time without worrying about connectivity and things like that. Cool, I've overstayed my welcome here. Thank you very much.